Okay, I just want to briefly recap on what we did last week or what we talked about. So it was the topic of digitization, and the question here was, how do we distinguish between analog and digital things, or the analog and the digital world? And then the question, how do we transform something from the analog world into the digital world, so that a computer can represent it and process it? And that was at the heart of this presentation. And what we have seen last week is that first we distinguished the analog and the digital world using this picture. So we said that on the left side we see the continuous world, where we can stand on each side, basically on the left side on any level. So it doesn't matter on that line from the bottom to the top. We could potentially stand anywhere, and there's an infinite number of points where we could stand. So any level is possible. And on the right side, we said that it's actually only 4 different levels, because we have these discrete steps. And that is the distinction basically between, or one property between, that's different between the analog and the digital world. Because in an analog world, we have the situation on the left side. We have different levels and all the levels in between. And we talked about what digitization then is. So digitization is transforming the continuous signal from the analog world into a discrete set of points, into a discrete set of numbers, basically. So we will see the examples that we looked at in a second. But I want to emphasize one more time, when we say a discrete set of points or a series of numbers, that doesn't have to be binary. That can also be like a decimal number. So once we transform something from the real world into a series of numbers, and that can be numbers in the decimal system, that's also digital already. So binary is just the specific number system that our digital computers work with. And that's why we usually, when we say digitization, we usually mean transforming it into a binary representation, but that's just because computers need the binary representation. And that's the reason why we almost mean the same when we say digitization. We say that's binary, but it's not true in the technical sense. Okay, then we talked about how we can then transform something like sound, and we said an example would be this meeting. So I'm talking into a microphone, and the microphone is doing exactly that. So it's somehow measuring the sound, which is an analog signal from the real world, and it's transforming this sound into a series of zeros and ones, a discrete set of numbers, and that then is being transmitted via the internet to your clients, and then when you have a speaker, it's actually reconverted into a analog signal. So it will be transformed into a sound wave again. And so we talked about what happens here, and we said it's basically for the sound, it can be represented using this picture. It can be depicted using this picture, and that's the picture of a sound wave. And as you all know, and as we talked about last week, a sound wave is sound is a wave that's propagating through the air, and we can measure the pressure of the wave, and we can measure the frequency of the wave, and that will give us basically all the information that we need to describe the sound. So the frequency is whether the sound is high pitch or low pitch, and the pressure is going to be the volume. And if we want to measure that, and we want to, for example, or transform that into a digital representation, what do we do? It's a continuous wave. So just to depict that here. So this wave, technically, any number on the x-axis here is possible. So there's no specific set of numbers. It can be any number, and we will get a y value for any of those infinite x numbers that we can choose. So we can choose to look at, this is 1 second, then we can choose to look at maybe, I don't know, 100 milliseconds. And it would also be possible to look at 100.76 milliseconds, and any number we can imagine from the real numbers. So it's basically infinite, but the problem is we want to transform it into a discrete set of numbers, because in digital we only have a finite number of samples that we can take. So what we do in the case of the sound wave is we decide how many samples, and this is per second. So we see the time scale 1 second as the example here. So we ask how many samples per second do we want to take, and then we distribute the whole interval of 1 second into even intervals of whatever, how many samples we want. So they are evenly distributed. For example, maybe it's 50 milliseconds, I don't know. And that is basically what we call the sample rate. So you may have heard that in the description of a sound file or the recording of a sound. It's the sample rate, and we said that, okay, if we have a higher sample rate, we are going to be closer to the real analog signal because we have more samples. But on the other hand, the file size will increase because there will be more numbers that we need to store. So higher sample rate, the higher the larger the file. But of course, on the other hand, the quality will also increase. So because we're getting closer to the original analog signal. And that's one important aspect. If we digitize something, we always, basically we can say always, lose information, because the analog world is infinite. We have infinite number of points, and we try to abstract away these infinite numbers into a discrete set of points, and we need to choose which ones we are taking and the other ones we're leaving out. And this is depicted by these gray boxes here. So the error or the information loss, you can imagine, is this, because actually when we look at this bar, we're going to measure this pressure, but in reality there's a curve that is describing the real pressure in this time interval. And this is basically, we lose all this information, which is the gray, smaller gray area. Okay, and then we also said in this case that we can choose how many bits we want to use to represent these numbers. And of course, if we have only a few bits, we can only store small numbers. So for example, with 4 bits, we could store 16 different numbers, and that would give us only so many options to differentiate between these 2 different levels. And of course, each bar is also a continuous value. So there's in reality, we cannot really distinguish discrete values here, but it's a continuous scale. But once we choose on the number of bits we have, we can, for example, if we choose 4 bits, which is very low, we would have to divide the scale into 16 different discrete steps, and then we would need to choose which one we're going to use to represent that bar. So we definitely want more than 4, but we definitely don't want too many, so that the file size becomes too large. And that's also a quality aspect of a sound file. How many bits we allocate to represent each number. So the bit depth is something you may have also heard before. All right, and then we did the same for images as another example. So what happens here? Basically, we have the real world again. An image is nothing than light that is, hitting some sensor or our eyes. And so the question is, how can we digitize that? And so represent it in a form that a computer can store and process it. And there we learned about this concept of pixel, or this list basically of color codes. And we said that we can represent an image from the real world by dividing it into these little squares, and we call them pixels. And the more pixels we have, the better the image quality, and the closer, again, we get to reality, because, again, in reality, there is no distinction into these pixels. So it's a continuous wave of light, again, in this case. And if we want to measure that, for example, in a digital camera, we have a sensor that has a certain number of those pixels where it can measure the light that is falling onto it, and that's how it gets digitized. So it simply converts the light that's hitting the sensor into a digital representation of that color, and then it gets stored basically as an array or a list of color codes in this case. And last time we have seen what we mean by a color code. So for example, the RGB code. And basically here again, if you have more pixels, the file will become larger, the quality will be better, but yeah, so it's closer to the real world. So that's the RGB code that we have introduced at this point. So that's one way how we could represent a color between 0 and 60 million different colors. And so the RGB code is widely used to represent colors, and it's a 3-byte code. So we need 3 bytes, 24 zeros and ones to store one color. And it's simply the parts of red, the parts of green, and the parts of blue that go into the final color that we're trying to represent. So this would be the blue of our university, and it's defined as the RGB code in decimal is 0, 158, and 227, and that's the same thing in binary, and that's the same thing in hexadecimal. And that's the code that we often use when we want to express a color, for example, in the web context. So that's how we do images. And then text is similar. If you want to represent characters, we learned about the ASCII code, which is simply a code system that assigns each symbol, each character, if it's a capital A or a small a, or if it's a special character or something like that, or even smileys and other Unicode characters. So every one of those gets a certain code, and the code here is written in decimal, but behind that the computer stores the binary representation, so zeros and ones. And every time we hit, for example, a capital A on our keyboard, the computer will be storing or receiving the signal of the binary code for that letter from our keyboard. And so we can also, in the same manner, store texts. So for example, a text document then would be nothing else but a series of zeros and ones. And if we know that this is a text document, we can then interpret the zeros and ones as being ASCII coding. And if we know the ASCII code, then we can transform that into letters, numbers, and symbols as depicted here. Digitizing temperature, another thing that we will also work with, basically sensors in the more general way. So a thermometer, for example, measures the temperature using a proxy. So for example, the electrical resistance in a material. It changes when we have different temperatures, and we can measure that. So we can measure the voltage that's running through the circuit. And as I said, the voltage will then change with different temperatures, and that's because the electrical resistance in the material changes. And if we know, so if we calibrate the thermometer and know at which temperature we have what voltage, we can then use it as a measurement tool to measure temperature. And that will be then converted into a binary representation using an analog digital converter. And then we once again get a series of ones and zeros, which basically represent the temperature as a number in the simplest form. And then the same goes for other devices. So basically, this is one example for a sensor, but we have many different sensors that work on a physical level, depending on what they measure, different, but the outcome is mostly the same. Some form of energy is measured using some proxy, and then we calibrate these sensors so that we can convert them into the unit of measurement that we're interested in. So that's just one example, but it works similar for other sensors. So for human input, it's also similar. For example, a button or joystick. So for a button, it's very easy. When you press the button, you close a circuit, and that will give voltage to the point of measurement, and then we can transform that into a 1, for example. And when there's no voltage at all, it's going to be transformed into a 0. So that's how our simple button that we have also learned about last week basically works. And then if you have a joystick where you don't have just on and off, but you have directions and maybe even strength, so how hard do you press the joystick into one direction, That's basically, again, a measurement of energy, and in this case, a measurement of force into a certain direction. So the direction can then be measured, and the force that is being applied, and then that's transformed again into digital representation. So if you want to know how different devices work, I referred you to that book and the particular chapter, Making Bits, from the book How Things Work Now. I uploaded that into ASCII. I think it's a very good book for very illustrative explanations. So they work a lot with pictures, and I think nice pictures that explain how different devices work. For example, touch displays and mouses, so mice that we use in our computers or keyboards. If you want to know how they work, this is a good reference to get a good idea about this. Okay, so the question or the interesting thing is, so digitizing things, I think we all have an idea about how we do that, and what the process looks like for different examples. But the question remains, so why do we do that? So it's still not clear. We haven't talked about it. So what's the benefit of digitizing something? So, and here we have 4 different aspects of digitizing something, and these are properties of digital goods, basically, in general, and we want to briefly go through them and talk about what that means. So on the left side, we see very practical properties. So the first one is, once we digitize something, it becomes computer processable. So it means a computer can work with that, whatever it is. So image, sound, signal from a sensor, human input, a text, whatever, a set of data points, it becomes processable by a computer. So that's a desirable property, but still it's not clear why. So why would we want to do that? I think the question, you can answer it for yourself, but it's worth talking about it briefly. So another practical property that we get is from having it computer processable, or even digitizing it only, we can make perfect copies of it. So it's perfectly reproducible. And that is because we have a discrete set of numbers. So let's say we converted an image into a discrete set of zeros and ones. And it's very easy to make a copy of that, even if we don't have computers. In theory, it's hard to lose information when we make a copy of that, because the ones and zeros will always be distinguishable. So when we make a copy, for example, and we made copies of sheets of paper, and we copy them over and over again, it will become less quality with each copy. So with the first one, we already lose some quality, and when we make a copy of that copy again, and then of that copy again, it will become unreadable at some point. And that's because in the analog world, we have analog signals, and analog signals are prone to disturbances. So for example, if we have sound, maybe that's better to understand. If we have a sound wave, and that's a wave propagating through the air, the recipient of that sound wave, in order to make a perfect copy, would need to have, and that's not even possible, but would need to have a complete representation of the sound wave. But since it's an infinite number of points that possibly could happen, that not possibly, but are part of the wave, that already poses a problem. But then the second thing is that, for example, if we make a copy of a sound wave, that's basically one way to record a sound wave was to put it on a magnetic tape, which is basically an analog medium. But with each copy of so if you copy an analog medium, for example, we make another copy of that cassette, we will just through the process of transmitting it over the wire, and it's very easy influenced by outside factors such as, I don't know, other magnetic fields, or and then we might get a different signal at the place where we record the copy than at what was actually played from the recorder. So there's an easy way to interfere with the signal, the analog signal. And We do not have that in digital, because in digital it's either 0 or 1. It's either on or off, and that's very easy to reproduce and very easy to transmit. And even if we have an analog transmission, such as a power cable. So a power cable basically transmits data using different levels of voltage. But we can still say, okay, if we want to transmit a 0 or a 1, we define a certain threshold. If it's above that, it's going to be a 1. If it's below that, it's a 0. Or we simply say, if it's basically the power is off or very, very little power, it's a 0. And if it's above a very high threshold, it's going to be a 1. And that's a very stable mechanism to transmit zeros and 1s, because you only need to distinguish between two options. Whereas if you have if you transmit via that same power cable an analog sound wave, the actual voltage will matter. So the actual voltage will be representing each point in the sound wave. And if you only have a very small disturbance here, it will disrupt the original signal, and what is received at the other end, we cannot know whether that's the original or if there's a disturbance, because we simply have to assume it's the original. We don't know if there was a disturbance. While it wouldn't matter in the digital representation, because there we would still not, probably through a disturbance, not exceed that threshold that's quite high, that would say it's a 1. And as long as we do not exceed that threshold, we can still interpret it as 0 and 1. So even if we transmit data in a digital way, it's much more secure, and it's basically 100% reproducible. And we can even have safety mechanisms to double check whether a signal has been disrupted when it was transmitted. For example, we could have a checksum at the end, and if that checksum does not match the bits that were transmitted before, we know something went wrong and we need to transmit it again. So that was a long explanation about perfect reproduction, but basically computers can perfectly reproduce an image file. So when we have an image file, for example, if we want to copy it, it's very easy to make a perfect reproduction. It's very efficient in computers to do that. And we don't lose any information. So that's the practical side. And then if we look at what are the economic properties that we get that are derived from those practical properties. So we have a non-rival good, which simply means this good is not consumed. So we can have as many copies of an MP3 file as we like. So for example, we record an MP3 file and we distribute it to our clients, to our customers. When we had the good old CD or DVD, there was actually the need to produce a CD, and we need to stock the CD. And then when the CD is sold, our stock is becoming smaller. And then at some point, there are no more CDs left. So we run out of stock. The product is sold out. This cannot happen in the digital world, because we simply make another copy in no time. So there's no need to stock physical things like CDs or images printed out on a piece of paper. So that all goes away, and products become non-rival. So we can have as many copies as we want, and we can distribute them very fast and easy using, for example, the internet infrastructure. That's the non-rival property. And then we also have the economic property of zero cost of reproduction. So not only can we make as many copies as fast as we want, but it's also at no cost. So there's no real cost associated with making the next copy of a product. So there's no marginal costs associated. We have fixed costs maybe. So we produce, and let's stick with the sound file. So a band is recording their music, and it takes them some time to come up with that song and play it and practice it. And then at some point you record it in a studio. But once you have it in a digital version, there are no more costs for reproducing it. So the fixed costs will become split across all further copies that are sold, and there are no variable costs added, no marginal costs. And so this is, of course, a very desirable property, because that will also, together with the perfect reproduction and non-rival property, give us a way to distribute it very fast, and also to a comparable low price, because there is basically no cost. So there is actually a small cost, of course, because we need to have electricity to power our computers. and we might also need to have storage if you want to store our original copies. But that again is only a very small fraction compared to when we want to produce physical goods, where we always have material going in that we need to buy. We have time that we need to invest to produce those goods, and we need machines that need to be repaired and so forth. And that's all costs that we don't have in the digital world. So that's 4 very desirable properties of digital goods, and that's from that we can derive many of the different business models around the digital transformation and digital goods that we see today. So these are very important properties that we need to understand. Then this is an image that simply depicts what I just said about the marginal cost. It's unfortunately only in German. I took this from a book that is in German, but I can translate it. So basically, Fixkosten, this is fixed costs, and this is variable costs. Here it's the same. And so on the left side, we see the typical situation for physical goods where we have the fixed costs. So we have here, that's the quantity of the goods that we produced, and that's the production costs that we have, the accumulated production costs. And we have the fixed costs, so that they will be there independently of the quantity that we produce, and then we have the variable costs that will be increasing in the physical world with each good that we produce in a linear fashion, usually in a linear fashion. So of course it's not always linear, but in this model it is. So we have to not only distribute the fixed costs to add the fixed cost to the price and distribute it to every customer, but also a set or a certain amount for variable costs. So this makes physical goods more expensive compared to digital goods, where we only have the fixed costs and there's basically no variable cost with each additional product that we produce. And basically, if we have, so if we calculate that and we have a large number of products that we're going to produce, we can basically almost offer our digital products for free. And that's why we see a lot of digital products also being given out for free, because so when you're in the software business, for example, it's you have the fixed cost, of course, of once coding and programming that software, and then maybe you have some maintenance costs, but basically you have a very so if you distribute it to a lot of customers, you have a large margin that you can play with to give away discounts. And that's what we see a lot in software. So when a company buys software, like an enterprise software, there's always the price that they set, but everyone knows that the price, this is basically just a baseline, and you usually get it for much less, because there's as I said, a large room for negotiations. While this is often not the case in the physical world, because there's a hard limit where you actually cannot go below a certain price, because otherwise you wouldn't operate efficiently. In the digital world, we see a lot of cheap or even free stuff that we can just for the matter or for the reason that we just talked about. So this is to depict it in a graphical way. This model, I think, is easily to grasp, even if it's not in English. The terms can be easily understood. All right, so what does it then mean when we talk about digitization and digitalization? So we said that we also want to address the difference. And here we have on the left side the topic that we talked about in this presentation was digitization. So basically to transform something into a digital format that has previously been in an analog format. And then that's what we technically mean by digitization. And what can we do then? So what's the benefit from that? So we can represent and store it in a computer, basically. That's and from there we can derive all these other properties like perfect reproducibility and zero cost of reproduction and not being consumed and stuff like that. So that's I think we have understood that. But what then is or what does the term digitalization mean? Because in German we don't even have the distinction. Here we would say it's Digitalisierung and digitale Transformation. So digitization and digitalization are two different terms in English, and in German we would say we mean by digitalization the digital transformation, which is often a term that you hear in the press or in the media. And how can we distinguish these two? So basically, the digitalization or digital transformation usually means applying digitization in a more abstract and broader sense. So for example, by that we often mean that we apply digital technologies to business processes, or apply digitization in a business context. So for example, if we digitize our online or our lectures like we do now, we would say, okay, that's part of the digital transformation. But underneath, we also do digitization, because what we need as a prerequisite to have a digital transformation is the real world in a digital form. And that's what happens for online lectures. That's what has happened in the music industry, where we digitize music, basically. We digitize sound, and from that, whole new businesses come up and make a business model out of it, and it's being distributed via the internet or streaming apps and stuff like that. So that's what we then mean. Okay, the whole thing, because we can digitize stuff, leads to a digital transformation of businesses, of industries, and that's what we basically mean by that. So when we talk about the broader picture, the more abstract picture, and the more global impacts of digitization, that's what we mean by digital transformation. So this affects services, processes, business, products, business models. So all these things that are transformed basically into a digital form, and therefore being digitally transformed. So what is then on the right side the question mark? So what is the goal if we have? So for digitization, I think it's very easy to grasp why we do it and what the benefits are. So it's these four properties. But what is the goal for digitalization if we look at the broader picture? So what do we want to achieve when we digitize services, business processes? So what's behind that? Maybe that's just not just one thing, but maybe you have ideas about that.
So one idea is to save money in that perspective, that you can exchange persons through machines.
Yeah. So saving money, you said, and the example was exchanging people that would need to be paid by machines, right? That's basically what okay. So saving money, reducing costs, basically. Yeah. So what else?
Maybe to save time as well. For example, when an artist wants to release music or something, they don't have to wait for the hard copies to be made. They can just stream it online or put it on a website or something like that.
So in this case, the time factor, so they can faster sell their product, right? That's basically what you mean, what you said. Yeah.
So and for safety reasons, so there are some jobs that are too dangerous for people, and machines can do these jobs.
Yep. Okay. So can you give us an example so it becomes clearer what you mean?
For example, in I don't know the name of the city, Fukushima or something, where the reactors, where the machines are upbound. They. I don't know how to say it.
You can say it in German then. That's it.
in Fukushima bauen Maschinen den alten Reaktor ab, zum Beispiel, weil Menschen sich nicht der Strahlung aussetzen können.
Yeah, so basically the machines do the job that's too dangerous for humans to do in Fukushima. So I don't know, abbauen. Does anyone know a good word for that? Decompose, I don't know.
Yeah, something like that.
The reactor and to yeah. Okay, so for safety reasons, we might want to. So basically, but it's not clear what is digitized here. So when you say it's a machine or maybe a robot that does it, that's still something we would assume to be a physical thing. But what is actually being digitized?
So the person is not on the same place. It's operating via internet with the machine.
Yeah. So basically, if you mean controlling it from a distance, and okay. But it could also be even autonomous, and then we would have the software or the program that runs the robot. That's the digital part in this case. But yeah, both would be equally digital. So, but yeah, okay. So that's saving money, save time for safety reasons. A lot of safe. So, but maybe more abstract or more general. So, what's the so behind all this basically is a more broader concept, even a more abstract term that we could name here. So, if you want to reduce the digital transformation and everything that you've just said to one term or one concept.
Maybe solving problems or automate stuff.
Yeah. So basically, what I was going for was automation or automating stuff, and that's basically telling computers to do all those tasks. So we want to tell computers how to do certain things so that we don't have to do them, or we as humans don't have to do them, or we don't things that we don't want to do, like you said, the safety reasons, or things that we can do less efficient than a computer, and we want to save time, we want to be more efficient. That's basically the broader picture, and it's all about automation, and solving problems is the first step. So basically you have to solve the problem. So how can you solve the problem, and especially how can you use a computer to solve the problem? So how can you tell the computer what it needs to do in order to perform that certain task, or to solve that problem? And once you have done that, you can automate it. And to automate stuff with a computer, the prerequisite again is that it's digital, that it's digitized, and that's true for processes. So at any point where you want to have a whole process being automated, you need to have it in a digital representation, for example. So otherwise a computer can't execute it. When there are analog parts in it, where you need human interaction or some other interaction from the physical world, that's where we will talk about some semi-automation, where you have parts are automated and then parts are still requiring a human interaction. But the broad term that we can put here is automation, and from there we can derive all these other things. So for example, when we automate something, we usually get more efficiency, we usually get less errors if we program the computer right. So if we do the wrong programming, then we might even get more errors because the computer does the wrong thing. But once we know that the computer is doing the right thing, it will do so flawlessly, so that it won't make any mistakes. So for example, once we know how to tell a machine how to drive, and we are sure that it works properly, we will have less problems on the streets, because it's simply not doing these mistakes that we do, for example, being tired and not paying attention, stuff like that. Computers just can't do that. They are bound to do what we tell them. And of course, you can always have hardware failures, but that's basically, again, a flaw of the physical world. So once you have it digitized, you can apply or you can automate it, and then that's basically the main goal of digital transformation.